Your game is a massive hit. 10 million players, of which 1 million playing at the same time. It's a dream come true. But there's a nightmare. Your real-time leaderboard for, let's say, top 10,000 players is getting hammered. Your database query, a simple select star from scores, order by score, descended by limits, limit can be 10,000, is running thousands of times per second. Your database CPU is packed at 100%, the entire game is starting to lag for everyone. This is a code red situation that can kill your game's success. So let's think about how do we fix this? How do we design a leaderboard that is built for this massive scale? So the problem isn't your database. Your database, whether it's Postgres or MySQL, is fantastic for storing data reliably. But asking it to sort millions of rows thousands of times a second is the wrong job for the tool. That order by clause that we talked about on a massive, frequently updated table forces a full sort operation on disk or in memory. At scale, this leads to intense CPU load, IO bottlenecks, and database locking. It simply cannot keep up. What do we need? We need a specialist for the job right now, right? So the specialist here can be Redis, and our primary tool is a data structure called a sorted set. A sorted set is an in-memory data structure that maintains a collection of unique members, where each member is essentially associated with a score. The collection is by its very nature always kept sorted by that score. So let's think about how does this work under the hood and why is it really fast? Why does it solve the problem? A Redis sorted set is brilliantly implemented as a dual data structure, a hash table and a skip list. The hash table maps members to their scores. Simple, right? That's what a hash table does, which gives us a fast order of one lookup for a specific player score. The skip list, which is a probabilistic data structure similar to a balanced tree, stores the members sorted by score. This allows for incredibly fast insertions and updates with a time complexity of O of log n, where n is the number of players in our leaderboard. So let's look at the commands. As you know, Redis has a lot of commands that we use. When a player gets a new score, we send the command zadd leaderboard score and player ID. Zadd leaderboard score and player ID. This log n operation means that even with 10 million players, updating a score is practically instant. Now, to fetch the top 10k players, we run this command. Zadd rev range leaderboard 0 to, let's say, 9999 with scores. The complexity here is order of log n plus k, where k is the number of players you are retrieving. So we pay a tiny cost, as you have seen, to find the starting element, the rank 0 player, which is the starting element, and then just walk the already sorted list to get the top 10k. It's not a sort, it's a simple fast read. So what does our final production architecture look like? A player gets a score. The game server sends a zadd command to Redis. The real-time leaderboard is instantly updated. Now, to ensure durability, we configure Redis persistence like AOF, which locks every write operation to disk. This protects us from data loss if the server restarts. Simple. So we use a write-aside caching strategy. After writing to Redis, our application asynchronously writes the score to our persistent SQL. Right? The database, the SQL database that we're talking about, is our system of record for long-term storage and persistence and analytics. But it is no longer on the critical path for real-time leaderboard request. All leaderboard reads from clients are served directly and instantly from Redis. Now what you have done, if you could see, is you have offloaded the real-time sorting to a specialized in-memory tool, and we have solved our performance bottleneck. Our database CPU is stable, the game is fast, the architecture is built to handle our massive success. And that is how you architect for scale. Hope you enjoyed and learned something from this video. Stay tuned.